what is issue 1? Right, so large D. In particular, you can think of D is much larger than N, right. So, D is the number of features and N is the number of data points. Okay. So, let us do some notational simplification. This will really help us, solving this issue well. So, let us start by giving some defining some matrices. The first matrix is the matrix of the data points. Let us say we have the data set which has x1, x2, x3 dot xn. So, let us say we stack these data points as vectors, d-dimensional vectors in columns next to each other. So, that is my data set itself represented as a matrix, which is a D cross n matrix. Now, the covariance matrix we know is 1 over n sum over I equals 1 to n xi transpose. Now, I want to write this covariance matrix in terms of this matrix that I have defined here, and that is possible, not too hard to see. So, if you look at x transpose now, which means that you are taking a D cross n matrix and then multiplying it with an n cross D matrix, which is the transpose of the data points, where the data points are all rows now. Now, this is exactly sum over I equals 1 to n xi transpose, right. So, this is perhaps you are already seeing why this is the case. If not, try to show this, right. So, show this exercise. All I am saying is that your covariance matrix, which is 1 over n sum over I equals 1 to n xi transpose, this summation can actually be expressed succinctly in matrix notation as xx transpose. That just implies that our covariance matrix is just 1 over n xx transpose, right. So, sanity check, x is D cross n, x transpose is n cross D, xx transpose is D cross D, which is also the dimension of our covariance matrix. Of course, we are dividing it by n, that is needed. I mean, standard definition needs you to either divide by n or n minus 1, does not really matter. We will stick to n, at least in this course. Okay. So, now what does PCA do? Well, PCA tries to find the eigenvectors and eigenvalues of the covariance matrix, or find the best fit line, which happen to be eigenvectors and eigenvalues of the covariance matrix. So, let us say Wk be the eigenvector corresponding to the kth largest eigenvalue of C, and let us call this eigenvalue lambda k. Now, you have a matrix C, and then I am saying that you take the eigenvalues of this matrix, arrange them in decreasing order. Lambda 1 is the highest, lambda 2 is the second highest, and so on. And Wk corresponds to the eigenvector associated with lambda k. Now, what is the equation that an eigenvector satisfies? An eigenvector is a special direction for a matrix, where if the matrix acts on this vector, it just scales this vector by some amount. It does not change the direction, right. So, the direction is either a scaling, it could reverse the direction, right. The scaling could be negative, that is still okay, but it does not change the direction. So, which means in equations, it means that C times Wk equals lambda k times Wk, right. So, that is the definition of eigenvector and eigenvalue, right. Well, now what we want to understand is, well, we want to find these eigen directions, which are W1 to Wk. Now, what can we say about these Wk's? Where do these Wk's live? Where do these eigen directions live? Of course, they are all d-dimensional vectors, but can we say something more about where these eigenvectors live? That's what we are attempting to find now. Now, for that, what we will do is we will replace C with its definition, which is sum over I equals 1 to n xi transpose times wk equals lambda k wk. Now, what I want to do is, this is basically algebra. I will retain this wk on the left hand side, bring the lambda k to the other side, and combine these xi and wk together. I can essentially bringing this wk inside. It does not depend on I, so it can go inside. So this whole thing becomes 1 by n lambda k sum over I equals 1 to n xi transpose wk times xi. If you are not immediately seeing why these two equations mean the same thing, pause this video, just work it out. You should be able to convince yourself that these two things are exactly the same. It's just one step of algebra. Okay. Now, if you stare at this equation for a while, something interesting becomes clear, right? So this is kind of saying, now let me actually, I can put this n lambda k on inside, right? So it doesn't really matter, right? So I'll tell you why I do this. Yeah, so both are exactly the same. It's a constant. With rest, it does not depend on I. You can pull it inside. Now, what is this saying? This is telling me that if I want the kth eigen direction, right? So eigen direction corresponding to the kth largest eigenvalue. Now, I can express that as a summation of some constant times xi, which means I take the xi data point, multiply it with some number, and then add up all these scaled versions of xi. In other words, this is essentially telling me that my wk is a linear combination of data points. So we are going to assume lambda k is not 0. Let's do that without loss of generality in this particular case. So because otherwise this is going to this is going to be infinity, and then that won't make sense. But for lambda k not equal 0, this is true. Now, the interesting thing is that, well, wk is a linear combination of data points, which means that somehow you need to combine your data points to get your eigendirections. Now, for different eigenvectors, the way you combine these data points are going to be different. Now, what we care about in PCA is to get these eigendirections, which means now we can say that equivalently we can care about getting these combinations of these data points which give these eigenvectors. Because once I have the eigenvectors, then I know how to get a compressed representation and all that. I can project each data point onto the eigenvectors. We know that. We know what to do once we have wk's. But now to get these wk's itself, what we are saying is that it suffices to find that combination of these data points that will give me the wk's, right? So what does that mean? That means that we can say our wk equals our matrix X, which is, remember, the matrix of the data points stacked in columns, multiplied by some alpha k for some alpha k in Rn. Now, what does this mean? This simply means that, well, remember, our data point is like this, right? So x1 to the matrix X is like this, x1 to xn. Now, I am saying there is some alpha k which is in Rn, which means that it gives some weight to each of these data point. The k says that it corresponds, these weights corresponds to the eigenvector wk, right? So alpha k1 to alpha kn. Now, if I multiply this, this is just sum over I equals 1 to n alpha ki xi. Of course, we know what this alpha ki is, right. So, this equation tells us that these weights are exactly xi transpose wk by n lambda k. But then to get these weights from this equation, it appears that you already need to know wk, right. So, this is xi transpose wk by n lambda k, you need to know wk to find wk. Well, that is a chicken and egg problem. We cannot use this equation to directly find these weights, because this equation needs what we are trying to find in the first place, which is wk. So, let us leave this equation out. We are saying here that, well, is there a different way that we can somehow find this alpha case? We first recognize that there are these alpha case, which exactly is this, but then let us forget that it is this for the moment. But if there is there a different way you can somehow get these alphas? Because if you know these weights, how should I weigh these data points to combine them to get my wk? That is all I need, right. So, to get my wk. So, somehow if I can get these alphas, then I am done, and there is an alpha k for each k, right. So, remember that, because for each wk there is a different set of weights. You have to combine the data points differently to get our wk's. Okay. Now, how can we get this alpha case? That is the how to get alpha case. Alpha k. This is the question. Once we have this, if we can somehow efficiently get alpha case, which does not require order of d cube computation, then we are in business. Because the whole point was our eigenvector solvers are going to take order of d cubed, where d is the dimension, d is the dimension or the number of features. If we can somehow get alpha case without spending d cube time, then that is a good thing to do, right. So, how can we do that is the question. Okay. So, we will do some algebra here. It's more the algebra, I will do it for completion's sake, but then what comes out of it is more important. But I would definitely suggest you to try and follow the algebra as we do it, right. So, we have wk is x times alpha k. We know that. We do not know what alpha is, but we know that there will exist some alpha, which is what we are trying to find, right. Okay. So, let this be right here, right. So, we know C times wk is lambda k times wk. That is by definition of the eigenvector. Wk is an eigenvector, it has to satisfy this. We wrote C as this, right. 1 by n x x transpose, this is something that we wrote earlier. We also are saying wk is x times alpha k. That is what we observed in just a minute ago. So, this is lambda k times x times alpha k. Okay, good. Let me bring the n to the other side and write this as x x transpose times x alpha k equals n lambda k x alpha k. Now, what I would do is at this step is pre-multiply this equation by x transpose. In other words, I am saying I will do x transpose times whatever was there equals x transpose times whatever was there, and what is there was x x transpose x alpha k, and we will see why this is useful in a minute, x alpha k. Now, if I rearrange terms, this is, I can do this, I mean I cannot, matrix multiplication is not commutative always. So, I cannot swap terms, but I can change the brackets, right. So, it is associative. So, I can change the brackets however I wish. In other words, I can do it as x transpose x into x transpose x. Basically, I am combining these two guys and these two guys into alpha k equals n alpha k is a constant that can come outside. This x transpose multiplies this x transpose x into alpha k, right. Now, this is a matrix, this is a matrix, this is a matrix. Now, x transpose x, now remember x was in R d cross n. So, x transpose x is in R, this is x transpose is n cross d, x is d cross n. So, this is n cross n, right. So, that is just to remember. Now, call x transpose x, just give it, let us just give it a name, let us call it k. Then this equation is k squared alpha k equals n lambda k k alpha k. So, we want the alpha k somehow, and we are saying, well, whichever alpha k that is, that you need to use to combine these data points to get wk should satisfy the equation k squared alpha k equals n lambda k k alpha k. Okay. In other words, if we can find alpha k that satisfies k alpha k, there is a k on both sides. So, I am saying if we can find an alpha k that satisfies k alpha k equals n lambda k alpha k, then we can multiply by k on both sides and it would have satisfied the other equation as well, right. So, which means that all we need to find is an alpha k that satisfies k alpha k equals n lambda k alpha k. If we can do that, then we are kind of done. Now, this looks like an eigenequation, right. So, this looks like an eigenequation. In fact, this is an eigenequation, right. So, basically we are saying that if you take alpha k, whatever this alpha k is, if I apply this k matrix to this alpha k, it has to scale this alpha k by n times lambda k, right. So, if I can find such an alpha k, then I am done, right. So, this is an eigenequation. Now, let us say I give you an alpha k, right. So, I give you something and then claim that that satisfies this equation, right. So, let us say I give you some vector u and then it satisfies this equation that k u equals n lambda k u, let us say. Now, well, is this u unique? No, right. So, now what I can do is I can do k times 2 into u will satisfy n lambda k into 2 into u. Now, what does this tell us? That, well, I can scale this u by any number and then it will still satisfy this equation. So, which means that we need a specific way of combining this data, these data points, right. So, a specific alpha that will give us a wk. We know that the length of wk is 1, right. So, we were looking for directions with length 1. Now, which means that there should be something that we can say about the length of alpha k also, or in general alpha k also. So, which means that you cannot arbitrarily scale this u that satisfies this equation and claim that all of these are alpha k's, right. So, now what is that? What does that tell us is what we are trying to find out. Let us try to find out how the length of wk gives us an indication of what is the length that we should look for alpha k, right. Well, what do we know, right. So, we know wk equals x alpha k, we saw that, right. So, we know that wk is some combination of this, which means wk transpose wk, which is the length, is x alpha k transpose x alpha k. Now, this is alpha k transpose x alpha k. We know that we are looking for wk's with the length 1, which means the left hand side is 1. On the right hand side, this x transpose x shows up, which is what we are calling as k, which means this is alpha k transpose k alpha k. So, now we are saying that, well, we need an alpha k that satisfies this equation, but it can't be any alpha k. Such an alpha k should also satisfy alpha k transpose k alpha k equals 1. If you find an alpha k that satisfies this equation, and if that alpha k satisfies alpha k transpose k alpha k equals 1, then that is the alpha k that corresponds to wk which has length 1, right. So, all this is algebra. All that we are saying is that we wanted wk, we are saying we can equivalently solve for alpha k, and solving for alpha k looks like solving for an eigenequation in k, but then the eigenvectors length is unspecified. So, we need to normalize the length, and then the fact that wk's have length 1 implies that alpha k transpose k alpha k should be 1, right. So, we should look for alpha k's eigen equations, but then it should also have this property. Okay. So, this is first point. So, which means okay. So, now we need one more important theorem from linear algebra, which will actually be very useful in understanding in solving, in completing this problem, right. And that fact, I mean, this is a linear algebra fact, or actually a theorem, but I will state it as a fact for now. And we will see why this fact is useful. So, essentially, before I state this fact, so let me say why we need this fact. Essentially, we wanted the eigenvectors of x transpose, but now we are saying we can solve the eigenequation of k, where k is just x transpose x. Now, somehow this also involves lambda k. We need to know lambda k, which is the eigenvalue of x transpose. But then we are only solving the eigenequation for x transpose x. So, now is there a relation between the eigenvalues of x transpose and x transpose x, right. So, because if we solve the eigenequation for k, that will give you a set of eigenvectors and eigenvalues. How are these eigenvalues related to the eigenvalues that you would have gotten had you solved the eigenequation for x transpose? That is the question we are asking, and the answer is this linear algebra fact. The non-zero eigenvalues of x transpose and x transpose x are exactly the same. So, now to make it precise, so x transpose is a vector, it is a matrix in D cross D, x transpose x is a matrix in n cross n. But because both of these come from the underlying x, which is D cross n, their eigenvalues are related. In fact, if you are aware of the singular value decomposition of matrices, then you can simply use that to prove this in 2 steps. I will not do that, feel free to try this. But what I am saying is that the non-zero eigenvalues, there might be 0 eigenvalues, because this is D cross D, this is n cross n, right. So, the maximum number of non-zero eigenvalues of these matrices will be the minimum of D and n, right. That is again a linear algebra fact. So, there are going to be a lot of 0 eigenvalues if D is large, but which there will not be corresponding eigenvalues in n, right. So, if n is smaller than D, there, and if your matrix has full rank, so then your number of non-zero eigenvalues will be n, and they will match with the top n eigenvalues of x transpose, which is a D cross D matrix, right. So, what does this essentially tell us, right? So, what is all of this telling us now, right? It is telling us the following, and this is the most important thing. We will now try to put everything together and see all of these together. So, we initially had C, which was 1 by n x transpose, whose eigenvectors and eigenvalues we wanted, right. So, let us say the eigenvectors of C were W1 to WL, some WL which we want, right. So, now for all k in from 1 to L, we know Wk is 1, the length is 1. Now, the eigenvalues corresponding to this are lambda 1, well, in fact, they are in decreasing order, lambda 1 greater than lambda 2 greater than lambda L. So, this is what we wanted to get. Now, let us look at x transpose. X transpose is just n times C. Now, what will be the eigenvectors of length 1 for x transpose? Well, they'll exactly be again W1 to WL. It's just the matrix is just scaled. So, the eigenvalues will scale accordingly, but the eigenvectors of length 1 will stay the same. The eigenvalues will be n lambda 1 greater than n lambda 2 greater than n lambda L. So, we need these W1 to WL somehow, right. Now, what are we saying? We are saying we need to solve an eigen equation of x transpose x, right. This is the matrix which we care about. Now, let us say the eigenvectors of x transpose x happen to be some vectors beta 1 to beta L, some eigenvectors. Now, what we know that all the eigenvectors length is 1, all of these guys are of length 1, and let us say now what are the corresponding eigenvalues? Well, now the linear algebra fact that I stated before says that xx transpose and x transpose x have exactly the same non-zero eigenvalues, which means the eigenvalues of x transpose x will also be n lambda 1 greater than n lambda 2 dot 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 greater than n lambda L, right. So, this we have, right. So, now what does this mean? This means that this is k, right. So, which means that k times beta k equals n lambda k times beta k. So, we have found an eigenvector beta k which satisfies k times beta k equals n lambda k beta k. Now, question is what we wanted? We wanted some alpha k which satisfies k alpha k equals n lambda k times alpha k. Now, here is something which satisfies, we found a beta k which satisfies k beta k equals n lambda k times beta k, but is beta k alpha k, right. So, can we solve the eigen equation like this and say is beta k same as alpha k? Well, we saw that there is a length constraint also on these alpha k's. It is not just the fact that it has to satisfy this equation, it also has to satisfy alpha k transpose k alpha k must be 1, right. So, which means now let us check with beta k, right. So, now what is beta k transpose k beta k? What is this value? If beta k was alpha k, then this has to be 1. But what is this? By the virtue of the fact that beta k is an eigenvector of k, so k beta k is n lambda k beta k. So, this is beta k transpose n lambda k beta k, which is n lambda k beta k transpose beta k, but we know beta k is of length 1. So, this is just n lambda k. So, beta k transpose k beta k is actually n lambda k. But then we wanted, if we set beta k as alpha k, then it is not going to work because then no longer alpha k transpose k alpha k will be 1. So, there is a scaling of n lambda k that is happening. So, which means we can set alpha k as beta k divided by square root of n lambda k. If we do this, now if once I set this for all k, now k alpha k will satisfy n lambda k alpha k 1 and 2 alpha k transpose k alpha k will also be 1. Why? Because alpha k transpose k alpha k is simply beta k transpose k beta k divided by the square root is multiplied twice, which is by n lambda k, but we know the numerator is n lambda k, that is what we argued here, divided by n lambda k, this is just 1, right. So, now this is kind of telling us how to convert your eigen solutions for this matrix k into the alpha k that we really needed. We will talk about why this is a useful thing to do, right. So, we are kind of going in circles trying to find alpha k, but then I will tell you why this is a good thing to do in a minute, right. So, now here is what is the algorithm that we are proposing, right. So, our input is just the data set D, which is x1 till xn, where all xi's are in Rd, and the assumption is that D is much larger than n, right. So, this is the setup that we are in. If we have too many features, that is where the time complexity is a problem. Now, what are we saying? We are saying that step 1, earlier we would have computed the covariance matrix and then we would have computed the eigenvectors and eigenvalues, we no longer want to do that because it's expensive. So, what is the step 1? Step 1, compute K equals X transpose X, right. So, K is in R n cross n. Step 2, compute eigen decomposition of K. Now, this is still an eigen decomposition, right. Well, we wanted to avoid a costly eigen decomposition, but then we are saying in step 2 we are doing an eigen decomposition of K. But note that K is an n cross n matrix, which means the eigen decomposition of K is only going to take order of n cubed. And if T is much larger than n, essentially what you are saying is that instead of doing a d cubed eigen decomposition, you can do an n cubed eigen decomposition, right. So, which might be much cheaper in general. So, we do eigen decomposition of K and we get eigenvectors beta 1 to beta L with corresponding eigenvalues corresponding to eigenvalues. These are eigenvectors n lambda 1 to n lambda k. Well, once you have done this, so this is an order of n cubed computation. So, once this is done, then we are almost done, right. So, step 3, we know that these beta k's are not exactly alpha k's, but then you have the eigenvalues also with you. This is still n lambda L. So, what you can do is set alpha k equals beta k divided by square root of n lambda k for all k equals 1 to L, right. That is it, right. So, once you have this, then you can get back your W's if you want, right. So, Wk equals x times alpha k for all k. So, essentially what we have done is we have gone in a different route to find our Wk's. Instead of directly solving the eigen decomposition, we are solving a different matrix, a related matrix, the eigen decomposition of which is cheaper, and then we are getting the eigenvectors and then converting that into the weights that you need to combine the data points to get the eigen directions of the covariance matrix. Now, this is pretty much solving problem number 1, issue number 1, because we are not working with a huge D cross D matrix, but then we are working with smaller n cross n matrix. Of course, this is helpful only if D is much larger than n. If n is larger than D, you might as well do the covariance matrix decomposition. But then we are in that setup where we are assuming that D is much larger than n, and then we are trying to do this. Now, so this solves issue 1, the time complexity issue. Now, note that you cannot, you cannot get away with the eigen decomposition completely, right. So, you have to do it, but then because there are only 2 important parameters in this matrix, one is D and one is n, we are just trying to make it as simpler as possible by picking the smaller of these. So, that solves issue 1. Now, we want to talk about issue 2 in the next video, but before going there, I would want to make one observation which I will again make in the next video, but then I want to hint it right at this point, and then we will come back and connect it to the next video. Now, what are we saying here? We are given this data set. The first step was to compute K as X transpose X, right. So, what is Kij in that case? Kij is Xi transpose Xj. You can verify that this is what Kij would be, right. So, for all Ij. In some sense, this is capturing, the similarity between Xi and Xj, right. So, in the dot product sense. More importantly, this also tells us that to solve the PCA problem, you only need these pairwise dot products between the data points. If you have that, you have all the information that you need to compute the PCA things, right? So whatever you want at PCA. We'll make this more precise next time, and then we'll see that this important observation of the fact that you only need this kind of a similarity between these data points and not necessarily the data points themselves always, plays a very important role in trying to use the solution of issue 1 to actually solve for issue 2, which is a totally different question, which says that what if the data points are not linearly related. It needs some creative thought to take this solution and then solve issue 2, and that is in fact one of the very important ideas in classical machine learning, and we'll talk about that in the next video. For now, I would want to summarize saying that all we have seen today is in this set of videos is to see how we have identified some issues with PCA, and then how you can solve the issue of time complexity by converting your original problem into a simpler problem in a computational sense, and solving the simpler problem will help you solve the original problem. We'll talk more about issue 2 in the next video. Thank you.